Welcome to this 5-minute quick tips webinar from Mentor Graphics, where we'll be discussing the benefits of having an MCAD embedded CFD analysis approach using FloEFD. In this first example, we'll be analyzing a vertically rising pipe built in Creo Parametric 3.0, as can be seen on the screen. On the FloEFD input data tree, we can see a flow rate at the bottom of the pipe of 150 CFM of water. The analysis objective is to understand the pressure drop of the system under these boundary conditions. We can see the Creo dimensions of the vertical rise of the pipe, which are available to us as we are using native geometry. When we examine the results, we can see a pressure drop of 0.5 psi under the specified boundary conditions. Let's consider a design scenario where the outlet of the pipe has to be raised higher. This is very easily handled with a CAD embedded analysis tool. The original sketch is simply edited to alter the vertical sections by inputting the new dimensions. The assembly is regenerated to make the changes to the dimensions. FloEFD will recognize the geometry as changed and prompt the user to reset the computational domain and the mesh settings, which we accept. All other settings have persisted and we do not have to start from a blank analysis again. Now we can solve the project with the updated geometry and have a look at the results. With the new pipe, we are now getting a pressure drop of 0.56 psi, which is higher than the first instance, which is expected. We can use the pressure drop data to size pumps for the proposed piping system. We can have a quick look at the results. On the screen are the flow trajectories of the water colored by pressure. By wireframing, we can see the gradual change in pressure as the water rises. We can animate these to show the flow dynamically. As we have seen, we can change feature dimensions and quantify the effect on the flow conditions using FloEFD. Now let's look at a more complex example of a ball valve. We can see all the parts which comprise the assembly in the Creo tree. Under the FloEFD input data tree, we can see we have boundary conditions of 20 psi on the inlet and 19 psi on the outlet, giving us a 1 psi pressure drop. The objective of the analysis is to understand the volume flow rate of water at various valve positions. We could incrementally change the valve angle ourselves manually, or we could let FloEFD vary the geometry using the parametric study. The Creo valve angle constraint is already specified as a family table parameter and available for quick import. We can import this dimension and set the min-max values of 0 and 60 degrees along with the number of desired steps, which is 4. The output parameters of interest is the volume flow rate. The parametric study will then create a scenario table of 4 design points which will become populated once the 4 projects are solved. Once solved, we can see the flow rate varying with valve position. As expected, when the valve is fully open, we have the highest flow rate. We can also export results to Excel to visualize the results in a graph. The other option we have is to use a goal optimization study. This time we would like to understand what valve angle will give us a specific flow rate. We again import our valve angle dimension, and under the criteria we choose our flow rate goal. We then choose a target flow rate of 10 gallons per minute, plus or minus 0.2 GPM. The software will then calculate a series of runs to zero in on the required solution. Looking at a project which is already solved, we can see 5 solves were performed, and design point 5 with a valve angle of 14.3 degrees gives us a flow rate of 9.88 GPM, which is within the specified tolerance for convergence. We have seen we can change part features, but also assembly constraints using FloEFD. In our final example, we would like to optimize the heatsink geometry on this LED cooler. Our design variables are the number of fins which have been radially patterned and the extrusion length of the whole heatsink. Let's use the FloEFD parametric study to optimize this. We will again start the parametric study and then input the dimension parameters for first the extrusion length. We find the feature in the Creo tree and select the dimension, which on the default model is 1 inch. We select 3 variants ranging from 0.5 to 1.5 inches. Secondly, we input the pattern parameters by selecting the 50 extrudes variable, which is the default number of fins. We vary the fins between 20 and 80 patterns. The LED temperature is selected under the output parameters. We can see all the design points under the scenario table. The completed scenario table shows the solved results. We can see the results easier in Excel and select the project with the lowest temperature, which is design point 5. We can see that a longer extrusion length with a lower number of fins is a better design choice in this instance. A quick look at the results shows us parameters such as the heatsink temperature and the airflow pattern all within the Creo window. This has been a FloEFD 5-minute quick tips video highlighting the benefits of an MCAD embedded CFD approach from Mentor Graphics. Please look out for our other videos.